In this video, we are going to talk about linear transformations. In particular, we're going to talk about linear transformations that go from Rn to Rm. We start by talking about linear transformations as a special class of functions that maps vectors onto vectors. So for example, if V and W are vector spaces and subspaces of Rn, then we can talk about f as a transformation or a function that maps from V, a vector space, to W, a vector space. This transformation will be considered linear if it follows these two or satisfies these two conditions. First, if you take the transformation of a vector u plus v, that's going to equal to the transformation of u plus the transformation of v. Second, if you have a scalar multiple, times u and take the transformation, you can factor out the scalar and take the transformation of just u and then multiply this by the scalar a, and these two will be equal. Once we've looked at a linear transformation, we'll look at how to represent transformations as a matrix. It turns out that matrices are linear transformations, and linear transformations that is, can be represented as a matrix. So we use this line over here, this equation, which kind of combines our two properties of linear transformations, but now we have our scalar multiple times our vector u plus another scalar multiple times a different vector v, and then we break it up. Since the scalar multiple by times u is just a vector, and this scalar multiple b times v is also just a vector, then by this rule here, we can break this up into t of au plus t of bv. And now, because a and b are scalars, we can use the second rule and break this up to atu plus atv. This equation here is going to be really helpful for us. First, because it'll tell us if we know how to transform a basis of a vector space, then we will know how to transform any vector in the space. And second, because it'll help us get the matrix to represent the transformation. We will do examples and cover how to make this matrix of a transform, but for now, I just want to go through this idea to give you a preview. So if you know how to transform a basis, then you know how to transform any vector in this space. What you do is you first write your vector that you want to transform as a linear combination of the basis vectors. Then this linear combination that represents your vector, you take the transform of that. In other words, you take the transform of the vector written as a linear combination of the bases. And then because the transform is linear, now you can convert your transform of your linear combination using this line up here to a linear combination of the transform. See how this now has the transform of vector u, transform of vector v, and it's a linear combination of the transform. So just imagine here, u and v are basis vectors. You write a vector as a linear combination of the basis vectors, and then you use this line here to transform it to a linear combination of the transforms of your basis vectors. And now we're going to go and back to our introduction, where we consider a special class of functions called linear transformations, and they map vectors to vectors. Also, linear transformations can be represented as matrices. Then if v and w are subspaces of Rn, then a function that goes from vector space v to vector space w denotes a function f whose domain is v and whose range is contained in w. Furthermore, for vector v and v, we write w is equal to f of v. Because this is a function, this is the picture that we often associate with a function. We go from a set A, in this case, our set is a set of vectors in the vector space V, and a set W, which is our set of vectors in the space W, and then the function will take V and map it over to another vector W. Our first example is a function f that takes vectors in R3 and maps them into R2. I can represent this situation pictorially. We have a vector in R3, so x1, x2, x3, and it gets mapped into a vector in R2, like y1, y2. An example is this function here that takes this x1, x2, x3 and maps it into x1 minus x2 and x2 plus x3. If I want to find the matrix that represents this transformation, because remember we said linear transformations can be represented by matrices, I'm going to look at my function and I'm going to figure out what it does to x1, x2, and x3. So I write out x1, x2, and x3. And I need to figure out what it does to x1 and x2 and x3 to make it equal to x1 minus x2 for my first coordinate and x2 plus x3 for my second coordinate. So here over at x1, well, for the first coordinate we multiply by 1. For the second coordinate we multiply by 0. For x2, for the first coordinate we multiply by -1. And for the second coordinate, we multiply by 1. For x3, the first coordinate we multiply by 0, and the second coordinate we multiply by 1. So here is our matrix. It is the 1, 0, -1, 1, and 0, 1. You can do this multiplication, this matrix times this vector, and you will see you will get exactly this transformation. And just to make sure we have a real example. So f will take the vector 1, 2, 3, and now we do the matrix multiplication by 1, 2, 3, and we get -1, 5. And you can also see that's exactly equal to x1 minus x2. So x1 minus our second coordinate is going to be -1, and then x2 plus x3 will give us our 5. And just looking over this, we talked about this is a transformation that maps a vector onto a vector. So here we have a vector in R3 and we map to a vector in R2. So it's a function that maps vectors to vectors, and it can be represented by this transformation because this transformation takes 1, 3, something in R3 into R2. And I also just want to repeat, when we said linear transformations can be represented as matrices, we did that by finding out what this function does to our R3 vector, x1, x2, and x3. And we went coordinate by coordinate. And then we took these column vectors and made them the vectors of our matrix. Now we've looked at these transformations, we want to formally define what it is to be a linear transformation. So a transformation T is a linear transformation if it meets two conditions. The first condition is the transformation of the sum of two vectors is equal to the sum of the transformation of the two vectors. The second condition is the transformation of a scalar times a vector is equal to the scalar times the transformation of the vector. Two other facts that you can verify: matrix multiplication is a linear transformation, and also if T is a linear transformation, then there is an n by m matrix, such that T is defined by, the transformation can be defined by the matrix multiplication, which we sort of did a little example of that here, but we're going to do a few more examples next. First, let's look at some functions that are not linear so we can compare. Now, I was almost going to object and say this certainly looks linear to me, but then I did the math. So let's look at f of one vector plus another vector. So let's just say f of x plus y. That'll equal to x plus y plus 1. Whereas if we plug in f of x, that's equal to x plus 1, and f of y is equal to y plus 1, then adding these two together is x plus y plus 2, which is not equal to f of x plus y. So that is why this is not linear. Furthermore, if I look at the second condition, so it's already not linear because it failed one of the two conditions, and it needs to pass both conditions. But it also fails the second condition. So if a is a scalar, f of a plus x will equal to ax plus 1, whereas a times f of x is equal to ax plus a. Looking at the second function, g of x equals x squared, and I decided to use u and v so it'll look more like this condition here. So if I put g of u plus v, I get u plus v squared, which is equal to u squared plus 2uv plus v squared, whereas g of u plus g of v is equal to u squared plus v squared. So it does not meet this criteria. Furthermore, it doesn't meet the second criteria either. If a is equal to a scalar, then our function would be a u squared, well, that would be a squared u squared, whereas a times g of u is equal to a u squared. Looking at sine of x, if I look at h of u plus v, that's sine of u plus v, which is not the same thing as sine of u plus sine of v, so this is nonlinear. And last, we have e to the x. So if we have k of x plus y, that's equal to e to the x plus y, e raised to the x plus y. Well, we can separate that to be e to the x, e to the y, which is equal to kx, ky. So far, actually, this condition holds. So let's look at the scalar multiplication. So k of ax is equal to e to the ax. Well, that does not equal to a e to the x. So this here does not hold, so this transformation is not linear. But now let's look at some transformations represented by matrices, because we are in, after all, linear algebra, and we are going to take that transformation we had looked at in a previous example, and we're going to determine if f is linear. The first thing I'm going to do is check this condition here, which I rewrote here. So I need to sum the two vectors and then take the transformation. That's how I will start. So here I have the sum of the two vectors u and v, and I know that we're going from R3 to R2. So u is a three-dimensional vector and v is a three-dimensional vector. So here I have u1 plus v1, u2 plus v2, u3 plus v3, and I'm going to take the transformation. According to my matrix, my transformation matrix, this is equal to x1 minus x2, so I'm going to take x1 and subtract x2. And then for the second coordinate, I'm going to take x2 minus x3, so I have plus x3. And now I want to rearrange my terms so I can see what kind of isolate the t, isolate the u. So I put my u's together, my u minus u2, my v1 minus v2, put my v's together. Here I'm going to put my two u's together, and then I'll put my v's together. And what I see is this is equal to u1 minus u2, u2 plus u3 plus the vector v1 minus v2, v2 plus v3, and this just so happens to equal to, according to our definition of our transformation, t of u plus t of v. So the first condition is met. Next, I'll check my second condition, which is about taking which I've rewritten here. So it's taking the transformation of a scalar times u and seeing if it equals to this right-hand side. So here I have a scalar a times my vector u. Again, u is a three-dimensional vector, so I have au1, au2, au3. Plugging in the definition of my transformation, I have a times x, or u1 minus a times u2. I have a times x u2 plus a times u3. I keep wanting to say a times x2 plus x3, but here it is. It's in u's. So I can factor out my a algebraically, just doing some algebra, and then because of scalar multiplication of vectors, I can pull out my a. So then what I get at the end is a times t, the transformation of u. So since both conditions are met, f is a linear transformation. My second transformation, h, takes vectors in R2 and maps them into R2. This is my transformation matrix. My first coordinate will be equal to x1 minus x2 plus 1, and my second coordinate will be equal to 3x2. And we're going to determine if h is linear. And we start by checking this first condition. We take the transformation of the sum of two vectors. So here I'm going to take the transformation of u plus v. So here I have, and again, u and v, since we go from R2, they're two-dimensional vectors. So u is equal to u1, u2, and v is equal to v1, v2. When I add them together, I'm going to get h of u1 plus v1, u2 plus v2. Plugging this into my transformation, I get x1, which is u1 plus v1, minus x2, which is u2 plus v2, plus 1. For my second coordinate, I get 3 times x2, so 3 times my u2, v2. I'm going to multiply by my negative and group my u's together and group my v's together. So I group my u's together and I get u1 minus u2. Grouping my v's, I get v1 minus v2. And then I also have this 1 out here. I group my u's together, 3u2, and group my v's together, 3v2. Looking at this is equal to u1 minus u2 over 3u plus v1 minus v2 over 3v2 plus 1, 0. So here I have h of u and here I have h of v, but I have this extra 1, 0. So in other words, h of u plus v does not equal to That's what this part is. And it does not equal to h of u plus h of v, because we have this extra term. And therefore, I can conclude that h is not linear. If we just want to know that h is not linear, we can stop here. But for completeness sake, I just wanted to show you what this half would also look like. So h of a scalar a times our vector u, we're going to look at what that looks like. So a times the vector u1, u2 is equal to au1, au2. When we take the transformation, we get x1 minus x2 plus 1. So x1 is equal to au1 minus x2 is equal to minus au2 plus 1. And at the bottom, we have 3 times x2. So that's 3 times au2. I can factor out my a's, and then I have a times u, but then I have this extra 1 plus 0. So here I have a times our transformation of u, but it's not equal to h of au because we have this extra term, 1, 0. Therefore, h is not linear. It fails both conditions. For our next example, we're going to let W be a subspace of Rn, and the 0 vector is the 0 vector in Rn. So we're going to define our transformation to take vectors in W into Rn, and we're going to say it takes these vectors and maps it to the 0 vector. And we want to show that T is linear. So again, this transformation just maps everything to 0. So let's take our first condition, T of u plus v. So T of u plus v, well, u plus v, no matter what u plus v ends up, it ends up being another vector in Rn, T is going to map it to 0. And 0 is equal to the 0 vector plus the 0 vector, which is equal to T of u plus T of v. So here, this condition holds. Looking at our second condition, T of au, so whatever this vector ends up being, T is going to map it to 0, which is equal to a times 0, which is equal to a times T of u. So this second condition also holds. So we have shown that T is linear. So the transformation that maps everything to 0 is a linear transformation. Now that we've discussed linear transformations, we are going to look at the matrix of a transformation. I have my definition of a linear transformation here for your reference, but we can kind of combine these two, and we can say that T of a scalar a times a vector u plus a scalar b times the vector v, this transform is equal to, well, because it's linear, au is just a vector and bv is just a vector. Because it's linear, we can break it up this way into the transform of a times u plus the transform of b times v. And now because of the second condition, we can break that into a tu plus b tv. So this is an interesting result. We can kind of combine these two into this one kind of more succinct form. And the reason why this is interesting is it tells us if you know how T transforms a basis in a vector space, a basis of a vector space, then you can determine how to transform any vector in the space, and we're going to use this fact here. To show you how that last statement here works, the statement being once you know how T transforms a basis, you can determine how it transforms any vector in the space, we're going to use this example. We're going to let W be a subspace of R3, and we're going to define it this way. The vectors in W, which we'll denote with the lowercase w, is equal to the vectors x such that the first coordinate is equal to the second coordinate plus 2 times the third coordinate. So an example of a vector in W, well, if the second coordinate's 1 and this third coordinate is 2, then that means the first coordinate has to be 1 plus 2 times the third coordinate, so 5. Again, that's 1 plus 2 times this third coordinate. So if this is the subspace W defined this way, then a basis for W is equal to W1, W2, where W1 is equal to 1, 1, 0, and W2 is equal to 2, 0, 1. And we'll talk about this a little more. I'll show you that it's a basis and why, but for now, just take my word for it. This is a basis for W. Now we're going to say we have a transformation on W. So it transforms W such that it takes our first basis vector and it transforms it to u1, where u1 is equal to 1, 1. And the second thing we know about this transformation is it takes our second basis vector and it transforms it to u2, where u2 is equal to 1, negative 1. Now that we know how the transformation operates or what it does to the basis vector, we're going to take a random vector, the vector w equals negative 1, 3, negative 2, and we're going to determine the transformation on this random vector. The first step is to express w that's negative 1, 3, negative 2, as a linear combination of w1 and w2. In other words, I want to take my w, negative 1, 3, 2, and express it as a scalar times my first basis vector, 1, 1, 0, plus a scalar times my second vector, 2, 0, 1. And I know how to solve this equation. I take my augmented matrix being first my matrix of coefficients, and then I augment it with this solution over here. I do my row reduction, and I get this is equivalent to this matrix here, which gives me, in this row, I have 1 times x2 is equal to negative 2. In other words, x2 is equal to negative 2. And here I have 1 times x1 plus 2 times x2 is equal to negative 1. In other words, x1 is equal to positive 3. So here I have negative 1, 3, negative 2 is equal to 3 times 1, 1, 0, minus 2, 2, 0, 1. So I have this written as a linear combination of my basis vector. So I deleted all the calculation and just moved my w is equal to a linear combination of my bases to give me more space to determine t of w. That means taking the transformation of this left-hand side is equal to the transformation of the right-hand side, which is what I have here. But now I can use the fact that t is linear. This is just a vector, and this is just a vector, so I can separate these out, and I get t of 3 times 1, 1, 0 plus t times negative 2, 2, 0, 1. And now because it's linear, I can also take out these constant coefficients. So I have 3 times t times 1, 1, 0 minus 2 times t times 2, 0, 1. Now I know these. These are my basis vectors, and I said we had that information of what t does to our first basis vector, which is equal to 1, 1, and what t does to our second basis vector, which is 1, negative 1. So now I have 3 times 1, 1 minus 2 times 1, negative 1, and I finally get 1, 5 is my answer. And it's worth noting there's no straightforward definition of t that allows us to just plug in a vector w and then figure out what the transform is. All we are given is how the transform takes these basis vectors and what it produces. So we must use the fact that t is linear. And what we do is if we want to find what t does to a random vector in our space, negative 1, 3, negative 2, the first thing we do is write our random vector as a linear combination of our two basis vectors, w1 and w2, which is 1, 1, 0 and 2, 0, 1. And now when we take the transformation, you can think of taking the transformation of both sides of the equation. But if you look at this is exactly what we have here. We have the transformation of a linear combination of two basis vectors. Here it's u and v, and here it's 1, 1, 0, 2, 0, 1. A linear transformation of our linear combination of basis vectors. And according to this, this formula here, we can break it apart, and this is the second step, until we have a linear combination of the transformations. And these two transformations are the ones we know. We know t of 1, 1, 0 gives us 1, 1. And now we just have a linear combination of our transformation. And the words I just said is essentially the same thing that we have on our overview slide. So I'll review it again, and I shrank down our example just for reference. So if you know how to transform a basis, here we have a basis, and we are given how to transform it. Then we know how to transform any vector in the space. So we write a vector, the random vector, as a linear combination of the basis vectors. That was the step here. And then take the transformation of the vector written as a linear combination of the bases. So in other words, we take the transformation of both sides. And this is the side that we're talking about here, the linear combination as the bases. And because the transformation is linear, we can use the fact it's linear to convert to a linear combination of the transformation of the basis vectors. So again, we use the linear combination properties till we had a linear combination of the transform of the bases vector. The way I like to think of it is W takes vectors in R3 and then it produces something else in R3. So I like to think of W taking some x1, x2, and x3. That is a vector in R3, and it produces this three-dimensional vector x2 plus 2x3, x2, x3. So how can we do that? So what is it doing with x1? Well, actually it doesn't use x1 at all. So for the first coordinate here, x1, it just multiplies it times 0. For the second coordinate, it multiplies by 0. And for the third coordinate, it multiplies by 0 because there's no x1 terms. What about x2? Well, for the first coordinate, it multiplies by 1. For the second coordinate, it multiplies by 1. But the third coordinate, it multiplies by 0 because there's no x3 term. And then let's take a look and see what it does to x3. So for the first coordinate, it multiplies by 2. For the second coordinate, there's no x3 term, so it multiplies by 0. And for the last coordinate, it multiplies by 1. So you can see if you multiply this out, this becomes 0, but you have 1 times x2 plus 2 times x3. That's our first coordinate. Our second coordinate will give us x2, and our last coordinate will give us x3. That means these two vectors, 1, 1, 0, and 2, 0, 1, will form our bases. The 0, 0, 0, you can add that to anything, and it's really not part of our bases. It's just the origin. So what we just did is we looked at this, how we could break up a linear transformation and we used this to say if we knew how T transforms a basis, we can determine how it transforms any vector in space. So the next thing we're going to do is figure out how to find our matrix of a transformation. And we'll do that to illustrate this using an example. Now we have a transformation going from R3, that is an x1, x2, x3 coordinate like this, to R2. And we know that the transformation on E1, and remember E is kind of our standard basis. So for R3, E1 is equal to 1, 0, 0, E2 is 0, 1, 0, and E3 is 0, 0, 1. And we know how this transformation transforms each of our standard basis vectors. We want to give a formula or a matrix for T now. And we're going to start very similar to what we had before. We're going to write our random variable x, which is equal to x1, x2, x3, in terms of our basis vectors e1, e2, e3. And since it's the standard bases, x is equal to x1 times e1 plus x2 times e2 plus x3 times e3. That means now we can take the transform of x, and that's equal to taking the transform of the right-hand side, which is x1 e1 plus x2 e2 plus x3 e3. Now using the fact that it's linear, first these scalars times e1 is a vector, the scalar times e2 is a vector, scalar x3 times e3 is a vector, so we can break it apart by the additions. So we get the transform x1 e1 plus transform x2 e2 plus transform x3 e3, and then x1, x2, x3 are scalars, so we can pull them out. So that's x1 te1 plus x2 te2 plus x3 te3. This is exactly like what we did with the previous example. And now we can plug in. So we have x1 times the transform of e1 is 1, 2. x2 times the transform of e2 is negative 1, 1. And x3 times the transform of e3 is 2, 3. So in other words, our transformation now then is x1 minus x2 plus 2x3, 2x1 plus x2 plus 3x3. This is our matrix, or almost our matrix. Our transformation matrix is just the coefficients. So it's going to be 1, negative 1, 2, 2, 1, 3. This is exactly our matrix that represents this transformation. And you can verify that by multiplying, doing this matrix, multiplying by this vector x1, x2, x3, and you will see you will get exactly this transformation. Another way you can think of this is T of T. You can calculate it by doing the matrix is equal to T of E1, T of E2, and T of E3. In other words, we could have just written 1, 2, negative 1, 1, and 2, 3. So again, summarizing that, Once you know how the transformation acts on a basis, you know how it acts on any vector x, and you can find the matrix just by simply taking the transformation on your bases and forming a matrix. And what we just did is encapsulated in this theorem. So if we have a transformation going from Rn to Rm, and we have our standard bases for Rn, then if A is the m by n matrix, we get T of E1, the transformation on each of our standard basis vectors, then this matrix here represents our transformation. In other words, our transformation is equal to matrix A times our vector x. I have this proof here for your reference, but as we're sort of trying to get through this overview fairly quickly, I'm not going to go through it. But I will do another example. Let's say we have a transformation from R2 to R3. So in other words, it takes a two-dimensional vector, it gives you this three-dimensional vector. This is our transformation. We want to find a matrix A that represents this transformation. From our theorem, we just need to find the transformation of our first basis vector. For R2, our vector bases is 1, 0, and 0, 1. So we need to find the transformation on 1, 0, the transformation on 0, 1. So we plug in 1, 0 into here, and we get 1 plus 2 times 0, which is just 1. We plug in 1, 0 here, so we get negative 1 plus 0, which is just negative 1. We plug in 1, 0 here, and we get 2 minus 0, which is just 2. For our second column, we're going to use our second basis vector, 0, 1. So plugging in 0, 1 here, I get 0 plus 2. Plugging it in here, I get 0 plus 1. And here I get 0 minus 1. So this is my matrix that represents this transformation. And I can verify this matrix represents the transformation by multiplying by a vector in R2, x1, x2, and I can see I get the exact same definition of the transformation. To review what we've done in this video, we talked about transformations as being functions that map from a vector space to another vector space. And we talked about linear transformations that satisfy these two conditions. One, that the transformation of the sum of two vectors is equal to the sum of the transformation of the two vectors. And two, the transformation of a scalar multiple times a vector is equal to the scalar multiple of the transformation of the vector. And we did several examples of this to show different transformations that were linear and transformations that were not. And when they were not, they didn't satisfy one or both of these conditions. Then we talked about matrix of a transformation, and that one thing about linear transformations is they can be represented as matrices, and vice versa. Matrices are linear transformations. For this part of our video, we used this identity or this equation here, which is sort of a combination of our two properties of linear transformations. We have t times a scalar times a vector u plus a scalar b times a vector v. Since au is a vector and bv is a vector, then we can use this first property to break this up into the transformation of au plus transformation of bv. Now, since a is a scalar and b is a scalar, we can use this next property to factor out our scalars. And this became really important. We did an example of this, that once you know how to transform a basis, then you know how to transform any vector in the space. And in fact, we did an example where we didn't even define the transformation explicitly, but we just defined the transformation in terms of how it affected the bases. That was our first example in this section. And then we said, okay, well then how can we transform some random vector in the space, knowing only how the transform affects the bases? And the first step was to write that random vector as a linear combination of your bases vector, and then you could take the transform of your linear combination of the bases vector that represents your random vector. And then you use this rule here, the fact that it's linear, to then do the manipulation and tell essentially you get the transformation of the bases vectors multiplied by scalars and then added together. In other words, a linear combination of the transforms. Last, we have this theorem here, which allowed us to find a matrix of a linear transformation. So that's it for this video. Thank you for watching.